Okay, afternoon. Hopefully everybody had a nice, refreshing break. Let's get going. Um, After this colorful presentation and stuff, this is much shorter, so we actually condensed the color palette only to 2 colors. So that's gonna help everybody who's also exhausted. Um, my name is Uri Elzur, and I work for Intel and also moonlighting on this little project with Srijit here. Okay, so let me introduce the consortium. The consortium is running for quite some time. At this point, we have a very large membership. The steering committee that actually started this is comprised of hyperscalers, system vendors, CPU, CPU, switch, silicon vendors, lots of experience across the board on networking. And when we opened up, as you could see, many has joined. I think it would be fair to say at this point that we have the whole network industry represented and actively contributing to this consortium. The reason we had to do a consortium, by the way, was to move faster. But with the pace AI moves and the pace industry agreements move, a little bit of impedance mismatch from time to time. We did start with the 4 horizontal work group that you see on the lower left. That is where specifications, starting from industry agreed APIs like Lib Fabrics, which we are actively extending a little bit. Others like MPI, SHMEM for HPC, but obviously not only for HPC. AI uses some of that as well. Those are left intact, unchanged. That is one of the design goals. Our key innovation happens in the transport, even though we have some optional features also in the Ethernet layer, which we'll discuss in a little bit of details. And one of the other design goals has been that this is supposed to work on existing data center switches, no changes, which obviously is conducive to fast deployment once everything is ready. So the innovation and the effort is mainly, but not only, on the endpoints, where in the response to a question before with more colors than what I can offer, obviously some is in software, some is in hardware, and you will see this. We are pre-release of 1.0, which really places some limitations on the details I can get into today. We definitely, this is only 20 minutes. If this is going to go well, one day in the future, we could talk a little bit in more details. First of all, GPU or accelerator-centric point of view. 3 key networks, you could see the different representative technical key figures of merit. Obviously, they are somewhat distinct and different. Many questions on can you get industry agreement alliance on all of them? Yes, no. You could see the difference in bandwidth in RTT per accelerator. That would be a good way to think about that. Standard data center with multiple applications, some older, some newer, some old infrastructure, some new infrastructure. What happens in the last few years, obviously, is that accelerator infrastructure are normally completely deployed, and they are a little bit more homogeneous, but also more importantly, they are restricted. At this point, we are talking about AI only traffic or HPC only traffic. And since the AI workload have more of a systolic nature, sometimes you have compute running and COM can run in the background, which you would like to hide. Some other times you have compute running, but the network is blocking, and exactly like Nandita, I don't want to be in the line of fire when that happens, so we are trying to get the network to be out of the way as much as possible. So the last comment on this slide is that what used to be the scale up was on a single operating system under a single piece of hardware, call it a server, is now growing a little bit. This is the network that has most of the traffic, as after this the traffic gets reduced to one level, and then you go for the scale up. So there were multiple reasons why Ultra Ethernet Consortium started where it is started. We have goals for both AI and HPC. AI and HPC, and for most of the folks here, I'm going to run really quick on some of the stuff because this has been regurgitated here so many times. So no need to take your time for this. But as an example on AI, people look at how much time is really exposed on the network exactly for those scenarios. AI, high bandwidth most of the time, but actually some other time, especially as the deployment and importance of inference grows, you also get some latency sensitivity, and you get significantly shorter duration of quote unquote the flow, which really means that you want to get your feedback loop closed much faster, call it congestion awareness. At the same time, the HPC community has different metrics. They are more sensitive to latency, to drops, and they are operating under different regimes from the API point of view because they are used to exact match, they are used everything in order, things like this. So the question comes up, can you actually make the two live together? Not only they measure the network differently, but can we find one solution that works for both of them at the same time? The answer to this is a long list of transport-specific features that are required for both of them. And then the little intellectual exercise we had was, okay, so if we are in agreement on those list of things, can we make them work together? As was pointed out before, the issue of tail latency, as we are talking about parallel processing, it's the last Johnny who shows up to the party that allows everybody to toast. Before that, you are sitting there waiting. So tail latency is critical for us. I'll touch on all of those features in the subsequent slide. I think it's very clear that those kind of requirements are good for both of them. And if you could do the two things together, high utilization along with keeping good control of your tail latency, then you get the good job completion time that we all want to get. So without bashing anyone, and hopefully you are aware of other older technologies around RDMA. One of the key messages I want to leave you with is let's separate two things. Let's separate the basic RDMA technology from the transport services that come with it. And when we say the transport services that come with it, we are looking at the whole space. Everywhere from the API without changing anything. So if you have a workload that runs on some popular AI framework, that should not see any change. If you have MPI, OpenSHMEM, whatever, that should not see any change. The other side of the bottom side of the stack, same stuff. Ethernet, and that's why the name was chosen Ethernet, because the message we would like to deliver is not only openness, not only interoperability, but also the full suite of tools the industry has developed over so many years, so that once this is out, deployment could be relatively fast. Some of the problems that we have all noticed, if you have problems with scalability that come from the state you need to keep in the endpoint. What was NNP to some people? In other words, I have a queue pair for each connection. What happens when I have many processes on many machines? What happens if I'm running on a single path instead of leveraging all the paths? But there are some challenges when you are trying to innovate and go multipathing. As an example, when I go multipathing, by definition, I have out of order. When I have out of order, there are two solutions, and I can take you back to the early 2000s for TCP offload. Those who remember how we were able to solve this without a reorder buffer. Reorder buffer does take delay, die space, latency, power, tail latency impact, etc. So you would like to have out of order without forcing the receiver to have a dedicated reorder buffer. You would like to have congestion control that does not come with too many knobs as some of those come with, and then you have every time you change something in the system, you have to change that. So these are kind of the challenges that actually affect the scale that the solution could get. So existing technologies at given scale, they would work. At other scales, they would not, or at a given cost in the implementation. Now, if you think about the first slide where we showed very high density as you get closer to those accelerators, it also means that I need to pack many NICs in those environments. So I would like those NICs to be as slim, as power efficient as possible. So some of the key design points, I'll rush through this. The next slide, we are going to give you a list of all the key features so that we wanted to make this as technical as possible, but given the shortage of time and the fact that as a ultra Ethernet policy, I do not get into how we do things too much until we release, which happens in the near future, it's a little bit limited. So this is first of all supposed to work at very high scale. And as I mentioned, we have lots of contributors on team that have lots of experience with it. Now, it's not that we think at this point, and I don't think the planet can support exactly 1 million endpoints. It's too much power, too much dollars, even for the larger companies here. But we are seeing already 100K, and what is really common is 10K and north of that. So we are ready to do this. As Nandita pointed out earlier, the idea of multipathing, but when you keep really high utilization of that is really key to scaling. Also for the tail latency. Now, what we did with packet ordering, instead of saying, oh, the old RDMA regime was I have to stick to one path, I have to do everything in order. MPI would require exact match. What we did is no. Let's look at specifically AI. When AI is doing a large bulk transfer, it doesn't really care when and not even how a given packet arrives to the other side. What it really cares about is that the message has been received once, has been completely received, no error, etc. By the way, we also have a mode where in order to achieve extremely high scale, we say, hey, I don't even need to send it once. I can send it multiple times. I would have a good information when the whole thing came in. That actually relaxes the scale on the receiver even further. For those of you who want to read a little bit about that, we have a blog that we released a few months back. This is a mode called Rudy. Not the most popular one by our standards, but we do have a mode that is called reliable ordered, and then we have another mode, reliable unordered. So you look at what the request coming from your popular framework, you say, oh, this one, I don't need to retain any order. You use that service supported by hardware and so on and so forth. maybe, that's easier for me to read. Yeah, so the optimized RDMA operations follows exactly the same logic. There's no queue pair. There are FML, call it connections requiring as little state as possible. There is little, also as little as we could tolerate on the wire as well. Security from day one, and yeah, I think the rest. Let's dive a little bit deeper here and talk about specific features. So starting from the top, we are linking ourselves to libfabric 2.0. That doesn't limit you to only this one, but as this is a consortium with a large industry representation, what we are looking for is something that is open source that can demonstrate the capabilities. It doesn't, and everything else that I'm going to talk about doesn't prevent you from having the ability to innovate as a vendor in your product. Innovation in the industry is good for everybody. There are going to be some extensions. One of the quick, easy examples for why we need extensions is because for the first time for the Ethernet industry, we are standardizing the switch offload. Obviously, the switch offload for collectives, which has value specifically for reduce, in some cases, get together, depending what you're doing there, has also been there for HPC, is valuable, but was not really standardized so far. A lot of effort going into that. Multipassing, we are actually able to send, you could call it a flow. It's really not a flow anymore. I get a request from, say, PyTorch, and that request is to do X, Y, Z. There could be a CCL library from a vendor. It could be that somebody does it differently, doesn't matter. That whole transaction now is really broken into individual packets. And each of them can travel its own merry way, and they get to the other side. And we have a way to adjust. We actually learn the situation of the congestion. Actually, there are two separate and related functions. Load balancing on one hand, not doing ECMP because that obviously has shown flow collisions and things like this. So this is done differently. Packets go their own way. Congestion is done the following way. There are two ways to do the congestion here. One is an improvements over what the industry has done, and that's one of the good ways to get a PhD these days. It keeps moving. It has to be programmable, and since we are looking also into the hardware implementation aspect of that, make sure that everything we do is programmable, but also fits the power and the time budget that one could have over there. So these happen in parallel. I did mention the ordered and unordered and the way we choose them. Another fun discussion in the industry in the so many years is lossy versus lossless. Many of the cloud guys are pushing for lossy network, and all the work we have done to date was focusing on the combination of lossy network or best effort, because lossy is not a nice word. Best effort with accompanying really fast congestion. Now, the congestion also needs a little bit more attention. The kind of RTT that we are looking into is much shorter. We want congestion to be highly reactive in those scenarios. You want congestion that allows you to run full bore from your first RTT before you have to send the network. You want to deal with unavoidable situation of incast. So why would you get incast? Not only because stuff could run out of sync, even though because of the systolic nature of AI workloads, your situation over there is so much better than when you're running a really multicolor data center traffic for many applications. But if I have a collective like all-to-all, well, sorry, there's going to be, I only have two strategies. One strategy is to schedule it such that I'm not really doing all-to-all, which really comes in the expense of latency. The other strategy is to actually let the network deal with it, but obviously now I'll get an incast typically on the last hop from the Tor to the receiver. For that end, we offer an optional receiver-based credit allocation that would allow you to make your own decisions how you would like to allocate the bandwidth. So all of those things are available, and as the proof normally is in the pudding, when we get to product in the near future, you'll see how much this is working or needs a little bit of improvement. Yeah, another nice little feature is streaming. Streaming that actually is available in some switches already is about trying to provide timely information to the sender about a packet that couldn't make it because we ran out of buffer space. So instead of completely dropping that packet and then you have to wait for the round trip loop to kick in, and we are counting on ECN, what you can do is just let the header go through. The header goes through to the receiver, then the UEC transport picks it up over there, send it to the sender. So even though I had a problem, I actually did communicate it, which really allows me to close the congestion loop even faster. On the network layer, pretty much as a little hourglass diagram. Yeah, don't want to change anything. We do have some optional features that we are adding at the data link. LLDP for negotiation. Link level retry. That's actually an important feature that we have seen in other technologies as well. As your bandwidth density increases, and as you are engaged in parallel processing, every connection or every participant that loses connection is slowing down the whole gang. As the set of endpoint grows, that importance is even higher. You don't want to be in that situation. The options are, okay, go back to software to retransmit, TCP-like, maybe not fast enough. Go back to your transport. Okay, so that may be a mix of hardware and software, maybe not fast enough. Okay, go to your immediate hardware. A little buffer in the hardware at the lowest level is doing that retransmit, and you do it when you need to. In HPC mainly, there's also been, but that's not the only application for this, there's been a need and use for high packet rate, which also cuts down latency. Now at 800 or 400 or whatever, okay, we're talking nanoseconds here, but it's also valuable in some cases. There are additional use cases as well. So, and to finally close on the question of AI versus HPC, we have profiles, which really means you could implement the whole thing if you want to. What we are going to use for compliance is really just those features. If you are focusing on AI, just those features. You want to focus on HPC and show, as an example, compliance with MPI. You probably are going to do additional features like exact match as an example, deferrable send, all sorts of popular features over there. So that's how you'll do that. How are we doing on time? Doing okay? So that is kind of, I think I covered all the different things over there. Okay. Maybe pause for quick questions if anyone had something. Yeah, go for it.
I have a question about trimming. So
About
trimming.
trimming, sure.
Yeah. So if there's a congestion and you're dropping the payload and letting the header through,
Right.
do you think having like an express pass like an approach where the header can pass through quickly, because otherwise it's going to experience the same head of line blocking at some other point? So basically, if there is congestion,
Is not true.
header is still going to have this head of line blocking at some.
Oh, okay. I got the question.
And in those kind of.
So, yeah. So
the question is
Yeah.
there any handling for trimmed headers? So trimming is fundamentally a process where packet that is going to experience congestion is dropped, and the header is allowed to continue with a bit that says this packet was not going to get delivered. The question is, can that header itself experience congestion?
So a very common little trick that you use is you simply put it in a higher priority class of service. You have resources assigned for that, and that's how you make sure. And actually, the spec itself was work of last week. The spec itself takes care of multiple situations because you could ask a follow-up question, which is wait. But I also have control packets. So which one has higher priority? And what happens? So yeah, we take care of this, but the basic answer is higher priority just to pass the through. And obviously, what happens is that when I get goes back goes at the transport. So in some cases, yes, there is a little bit of rototilling where information at this layer goes back on another, but okay. I think actually, yeah, we could. I covered all the verbiage over here. So if you want to cover, because one of the key thing is, yeah, maybe this summary slide, and then we go to a specific. Sorry. Yeah, no, that comes. So this is kind of your cheat sheet type of a summary. What we are doing different. What does it? What is kind of the expected relief or performance improvement for that? So multi passing instead of a single pass. Flexible order, we discussed that where there is a choice. You leverage that when you can. When if you want to keep more strict policy, you could do that. The congestion, we spend lots of time right now to standardize the way the endpoint and the switch work with the offload. So the key point over there is trying to minimize both the traffic on the wire as you set it up and as it runs, including obviously error cases, as well as the state that needs to be stored in the switch in order to support that. You basically can do that in two different ways. One way would be to oversimplify a little bit, RDMA write style. The other way to do that could be an RDMA read. So in other words, the question is who's the initiator, who's controlling the transaction. And for simplicity, we are starting with the write, so the endpoint is actually pushing into the switch. We discussed the simplified RDMA. It is simplified on multiple ways. It is, first of all, we are not behooved to do RC that has scaling issues. There's no real queue per. Hopefully, we scrutinize good enough the amount of state that needs to be kept, because some of us coming from embedded development in Elzur would like to see it as minimal as possible. One of the nice challenges we also had has to do with security. When you start scaling, so everything in the industry that we've found so far, okay, so I can create some and integrity that goes and confidentiality that is really based on point to point. But what happens when we scale to that large number? So the solution that we came up with is a solution to manage the keys in some sort of optimization on KDF. Anyone here who has some security interest is welcome to come and criticize that, because more eyes on security is always better. And yeah, I think we talked about the scale. So with that, Srijit, you want to talk to this before we wrap up the session?
I thought I was only going to come and collect the applause. Thank you. We are done. So this is it's not much more information. The idea is to show what we are building from a software perspective. And so this is literally the whole stack up, right? What's shown in blue is what's called the provider layer. Unlike an RDMA application, now we are going direct to libfabric. Advantage, or the point being, that you eliminate one more layer of thing that you have to intercept and manage. Like any other RDMA device, the green driver is your resource manager. It does all of the initialization, sets up the queues, gets going. And the direct data path is a kernel bypass path. The current project, actually, which we still also can't share for the same rules and the reasons that Uri mentioned, has a software implementation of a device. There's a device model and a driver that comes as part of the package. Device model, as Uri was saying, has these things called packet delivery context, which is the NIC pipeline, and an orthogonal layer called the congestion context, which is the congestion management state, that then goes out to real port. So what is shown here, the diagram that's shown here, is a real working system that does end-to-end connection, where an application sees a UET device, opens a UET connection, and talk to the other side using ordered or unordered semantics. And as listed in the text, if you have the time to read it, it uses Netlink like everybody else for doing initialization, with a bunch of out-of-band communication mechanisms for doing connection establishment. That is actually still work in progress. And then we are hoping not to repeat the wonderful world of CMs, and then kernel bypass on the data path. I think that's all I really wanted to cover. And yeah.
So just to bring it together, so obviously the incentive here is to start working with this community, kind of high level schedule. What is gating the release date? There's no, it's not like let us put a stake in the ground and we must be there. What's happening is that when the different specs, and this is going to be a few hundred pages long of a spec, because it covers all of those layers, when they reach the right maturity, then we move to the next phase. At this point, we have some of the specs are already what you could call frozen and going through the legal phases of ratification. Others are making their way, and so we do expect official release either towards the end of this quarter, early next quarter. Those are realistic times. Bear in mind that the critical tenets of the architecture are stable for quite some time, and that is also experience gathered from other standards and open source community. What you want to do is you want to get all the stuff that needs to be baked in hardware eventually. You want to get that as stable as possible, as early as possible. And if we argue over an error code in libfabric, which is really what discussion going on as we speak, that is not a very big deal. If you move even a bit in the header, hardware can deal with it very nicely. So that's actually our timeline. We have been in operations for about 2 years. We were all hoping it's going to be faster, but it doesn't. That's the reality of the industry, and hopefully we get to collaborate now closer, because some of it is available already in running software, not in performance. And in order to usher in products that some of our members are already working on, which you will see in the market soon, we want to engage with this community.
The thing I wanted to clarify is that when 1.0 is available, that's when it'll be an open spec. Right?
Yeah. Sorry if I failed to mention that. So the way we work is that yes, when 1.0 is out, it is open, free download for anyone. So it's not limited just to members, but obviously you're welcome to join. And we have many that elected to do that already.
Not everybody at the same time.
No, everybody is already overwhelmed.
Yeah. Okay. There are no questions. We'll close the session. Thank you, Uri.
Thanks.
And thank you.